How do you think our universe began?
Well, scientists have a creation story. It's not the same as the Bible. It's not the same as other great religious works. It's a very hot, dense state 13.8 billion years ago. And as outlandish as it sounds, there's really a pile of evidence to support it. And in fact, if I was being bold, I would say that the status of the Big Bang as a theory of science is right up there with Darwin's theory of natural selection. It's maybe not as commonplace knowledge to most people that scientists think they know how the universe started a long time ago. But actually, the evidence just keeps piling up, and it's really hard to avoid the conclusion that 100 billion galaxies and all the stars and planets and people and things they contain were once squashed into an area smaller than an atom, because that's basically what it says.
And yet some scientists have the gall to question it. What are they seeing in the theory that makes them think that it is insufficient?
Right. Well, so there are subtleties to it, and you have to dig a little deeper. So the basic picture that our universe was smaller, hotter, denser in the past, and enormously so, I think that is really hard to refute. However, the full story of cosmology has ingredients in it that we think we have evidence for, where there's a lot more debate. So the universe is mostly made of dark matter and dark energy, and both of those are puzzles to astronomers and to physicists. So it's fair enough to say, well, you guys don't really know what you're doing because there's all this dark matter and it's more than all the regular stuff and you don't know what it is, although we've ruled out a lot of things and we're kind of homing in on what it might be, subatomic particle basically. And then dark energy, where, truth be told, all bets are off. That's the thing, the entity that is causing the universe to expand faster and faster at an accelerating rate. And there's one very solid piece of evidence that that's what the universe is doing. But as for what's making it do it, this thing called dark energy, really we don't have much idea. So that's true. There are pieces of this picture of cosmology that are still up for grabs or argued over and so on. But I would separate those out from the basic picture of the universe starting from a hot, dense state. It's really hard to refute that.
Okay, so the Big Bang remains the best explanation we have for the beginning of the universe as we know it today. My question then is, can it explain how the universe started, or does it only work from a certain point on?
Right. We inevitably ask questions beyond what we can explain. So the Big Bang does beg other questions, like what you said. Why did the universe start? I mean, why? That great philosophers have said, why is there something rather than nothing? It's a pretty good question still. So what caused the Big Bang, or what was before the Big Bang, or what was it really like if in this incredibly unfamiliar physical state? And so, when scientists are being honest and, not full of hubris, they acknowledge the limitations of their theories. But within those limitations, they're fairly confident. So the Big Bang doesn't give a reason for why it started, doesn't talk about the precursor state or what was before, doesn't say why. Science tends not to answer why questions, tends just to answer how questions. So if we just limit it to saying the Big Bang is a theory or a model that describes the evolution of the universe from a very, very hot and dense state 13.8 billion years ago, it does a very fine job. But when we ask those deeper questions, we have trouble. But it doesn't mean we can't ask them. I mean, we might hope for a better theory that actually does answer those questions. Now, it won't be massively different, though, because it's still got to account for the fact that we see evidence that the universe was smaller, hotter, and denser in the past. You can't get around that.
What do you think are the most compelling theories?
So the most compelling augmentations of the basic picture are the idea of inflation. So there are puzzles about the properties of the universe that also beg for an explanation. One is, why is the universe so flat? Space is flat, as well as we can tell, very, very close to flat. And why should that be a surprise? Well, it's a surprise because Einstein's theory of gravity that accounts for the expansion of the universe deals with curved space-time. And when everything was all on top of everything else, space-time should have been very curved. So there should have been a lot of curvature at the beginning, and yet it went away or was stretched out. And so inflation was this idea developed 40 years ago, actually quite a while ago, to posit a super fast inflationary exponential expansion in the first tiny fraction of a second that essentially flattened out space, also ensured that the universe would be basically smooth. So the radiation of the universe is very smooth. The intensity is the same to 1 part in 1,000% in the sky wherever you look. So the inflation idea accounts for those things which would otherwise not be naturally explained by the Big Bang. So that's the biggest embellishment or augmentation of the Big Bang. Now there's some other people who've been trying to finesse away the origin problem. So the origin problem is a problem. Like, what is this infinite density and, you know, infinite temperature? What does that mean? Of course, it doesn't mean anything. It's non-physical. So there are a few modifications of the Big Bang theory that actually they sort of finesse away the Big Bang itself as a singularity, as a sort of infinite state. And they allow, in practice, actually, for a bouncing universe. They bring back that old idea of an expanding universe that might one day recollapse and then re-expand and recollapse. So there's some, you know, these are newer ideas, bouncing universes and so on. Again, they don't avoid the fact that the universe we're living in right now seems to have had a certain history that we can measure, but they place it in a much larger context where you don't have to have an origin and that's it. And it's part of a process that may repeat and repeat, which is an interesting possibility.
When you were talking about dark energy, you said that all bets are off. I don't know if you're a betting man or not, but where would you put your money on what it is?
You know, it's off in the sense that I wouldn't know where to put my money. With dark matter, I know where to put my money. Most people think, you know, just to digress into dark matter for a while, because it's not a success in the sense that we know what it is, but we've ruled so many things out that it's narrowing what it could be. If you want to place your bets, you've only got a few choices. It's not black holes, it's not planets, it's not rocks in space, it's not tiny dust particles. We've ruled out all the big dark stuff pretty much down to subatomic particles. And luckily, the physicists, in their own work on the standard model of particle physics, have thrown out a few candidates that could both explain some of the problems they have in particle physics and the problem of dark matter. So that is progressing, and there's a lot of experiments to look for it. Dark energy is way more problematic because this is like, you know, at the level of high school physics or whatever. You have evidence that the universe is accelerating in its expansion. So something that essentially works opposite to gravity, because gravity pulls things together, and this is making space leap apart faster and faster. That's what dark energy is. So the phrase itself is just a phrase, a container for ignorance, if you like. As far as what dark energy is, there's literally hundreds of theoretical papers a year, because the theorists are having a lot of fun with this, because the observers haven't given them anything to go on. That's the only good evidence for it, is that accelerating expansion. The theories go to string theory and wild new theories of gravity. They go well beyond general relativity, and you know, it's a wild west of theory, and it's very, like I say, in the bet game, I wouldn't know how to place my bets. They sound wonderful. It's like going into an ice cream shop where there are these thousands of wacky flavors, and oh, which one do I taste? You know, which one do I like? I don't know. They all look good to me. So basically, in science, theory has to be constrained. You know, the crazed dreams of theorists have to be constrained by observation and data. And we're in a very data poor situation for dark energy. That's the real problem.
I'd rather be in the ice cream shop than the Wild West, I think. But yeah, I get both metaphors. You know, for the layperson, for someone with pre-university understanding of physics, what is dark energy? What is the problem that we're trying to define? And why is it proving so hard?
So the manifestation, which is, you know, why you believe it is worth talking about at all, is the accelerating universe. And that was doubtful for a while. It's 1990s, mid-90s, when that first evidence came up. Two groups competed with each other vigorously over that measurement. It led to a Nobel Prize. So, you know, a lot of scientists think what they saw was real and is actually happening. And then you start to wonder, well, what is it? So it's a property of the vacuum, apparently. It's not a new particle per se. It's something to do with space-time itself, a property of the vacuum of space. So for a while, you know, immediately you have a possible answer. The physicists go, aha, the vacuum does have energy. So it's been known in quantum theory and in in the world of physics for a century, that what we think of as the vacuum, empty space, actually has a tiny bit of quantum energy. That's part of quantum theory. It's very small. And so you chunk through the math and you see, well, could this tiny vacuum energy that we've known about for a while in physics, could that be the energy that's making space-time accelerate in its expansion? And when you do the math, you get very excited as you start. And then when you do the math, the number is wrong. It's wrong by not like a factor of 2 or 50%. It's wrong by 100 orders of magnitude. And that's a big oops, even in the theoretical physics world. So the vacuum energy entity, the thing that we know of in physics that's a real thing of the vacuum, fails miserably to account for what the universe is doing. And so you go back to the drawing board, and that's why you get the Wild West of theories and ideas, because you're trying to, you're reaching for physics we don't know yet. And physicists know they have work to do. We don't think the standard model of particle physics is the final answer. We've looked, Einstein spent 20 years, and physicists have spent another half century trying to merge gravity with quantum theory. That's the holy grail of physics. And so there's a thought that out of that merger, out of that unification, the answer to dark energy will just drop into your lap. But there's actually no sign of that happening yet, so it's not clear that it will.
You touched briefly earlier on the fact that scientists, provided they haven't got caught up in hubris, will accept the limitations of their theory. Do you think hubris has been an issue in modern science?
Oh, yes, definitely. It's always an issue in science. This is a crass analogy, but you can't smell your own farts, so you just, people who work on, especially theoretical physics, they're very smart. This is rarefied air of mathematics and physics. And, when they have successes, they're amazing. The standard model of particle physics itself led to 12 Nobel Prizes over a period of 2 decades. It really was foundational work. And so when physics at that level of ultimate physics succeeds, it's very impressive. And I think that naturally can make people a little overconfident. And so physicists they're not all monolithic. Some physicists are suitably cautious about theories and skeptical. Scientists should always be skeptical. Some scientists perhaps are not skeptical enough in this arena, and some scientists view the track record they've got as it probably does make them overconfident about the projection of theories into the future. Ed Witten, who's been dubbed the smartest man alive, it's like one of the things Time magazine would call a physicist that they interview. He is a very smart particle physicist. He, in a moment of true honesty and modesty, he said, we just may not be smart enough to figure this stuff out, by which he meant string theory or unification of gravity and the other forces. So I don't know if that's hubris, but the people doing an activity, if you're a painter or a musician, you don't like to be told, well, that's impossible to paint. You can't paint that. Or, well, you can't play that scale or that piece of music. It's impossible. Just give up. Don't even try. So scientists don't like to be told that either. They don't like to think it's impossible, that they couldn't do it because they're not smart enough or because we don't have the tools. Sometimes we just don't have the tools. An example on that, general relativity, which is incredible intellectual achievement of Einstein, that language, and that did not emerge for a while after it could have or should have, because the tools did not exist. Einstein had to reach into the mathematics of crazy Russian number theorists of the 19th century for multidimensional curved space-time, pure math. He reached back into some pure math that was lying on the shelf in books, and he molded it into a physical theory. And so physicists often have to invent their own tools or repurpose mathematical tools before they can even make progress on a problem. And it's very hard to predict how that's going to go in the future.
Let's build on that in a slightly different way. You've traveled to India to teach science to Buddhist monks. I'm interested in the overlap between Buddhism and particle physics, where there is one.
Right. Well, before I went on my first trip out there, this is now 10 or 11 years ago, I had in my pocket, to read on the plane, Dalai Lama's Universe in a Single Atom. And that was a book he wrote, I think, in 1995. And it's a beautiful exposition of, the potential alliance between Buddhism and modern science, and he doesn't overplay it. Sometimes people force these things, and you can tell when they're forced. He didn't force it, and he's learned a lot from all the dialogues he's had over the years. So I was excited by that, to read his book, and then I was even more excited when I realized that down there on the ground in a monastery or nunnery, we taught nuns as well as monks, that they were very savvy about physics. They, not in a technical sense, but they at the ideas level. So Buddhist practitioners in the traditions that I was teaching in, they're exceptionally sophisticated in their ways of thinking about problems, as philosophers basically, and as logicians and rhetoricians. So they, they are very able to grapple with exactly the issues that physicists have to grapple with too, and cosmologists. Where did the universe come from, and what does mass mean, and all the foundational questions that scientists are still, they love that stuff. They go straight there. Whereas, to be honest, when I'm teaching freshmen or 18 or 19-year-olds, they sometimes get a little skittish about that stuff. I mean, they're worried about grinding through the math and solving the problem set that you just gave them. They don't really go straight to the deep philosophical questions. But these monks and nuns, boy, they go straight there.
So you went there to teach them science. What did they teach you?
Patience, not an imperfectly learned lesson. They have a pretty hard life. I mean, they're poor. It's dirt poor in northern India, where they're in settlement camps and so on. They've been given plots of horrible land, which is cheap land that was available to them. So they have a hard life, get up at 4 or 5 in the morning to pray, and and they're working through the evening. If they do academic stuff, they're working 17, 18-hour days. So I learned from them that you can be intensely applied to whatever it is you're doing, whether it's studying astronomy or your prayer tradition, and be incredibly patient with it. Just have sort of infinite well of patience. That's just a really hard lesson to get. But also be immediately light, not take it so seriously that it squeezes the fun out of life. They're never far away from a smile or a giggle, or the whole class just sort of breaking down and falling around in laughter over something that seemed pretty mild to me. I don't even know what triggers it sometimes.
Sounds like something we could all benefit from.
Yeah.
One of your recent books was Einstein's Monsters, The Life and Times of Black Holes. What can black holes tell us about the origin and the future of our universe?
Well, probably more than we know at the moment. We're still learning about black holes. We don't know much. We know they exist. I think the evidence for black holes on a range of scales, not just the dead star black holes, but these huge black holes at the center of galaxies, it's really good. And so nature knows how to make black holes as big as 30 billion times the mass of the sun and as small as a few times the mass of the sun. That's amazing. In the Big Bang and the story of our universe, there's a fascinating chicken and egg question of which came first, the galaxies or the black holes they all contain, because it's possible that the early universe was seeded with primordial black holes, or black holes that then aggregated matter around them. And that would be kind of cool. That would sort of place black holes in the driver's seat as being, the instigators of all the building of galaxies and things that we see in the present day universe. In terms of the end story, they're the last man standing, last woman standing, if you like, because when the universe is sort of dissipated, if it continues to accelerate in its expansion as we expect it will, stars will all die, boo-hoo, no stars. Life doesn't have to die because there's plenty of energy in the universe. After stars die, we can get gravitational energy from a black hole, for instance. And in fact, that would be the final repository. So black holes are not quite immortal. If Stephen Hawking is correct, eventually they will evaporate and there will be literally nothing left but the void. But for this long future of the universe, including the future after stars are dead and it's a dark universe, all the action, all the fun is going to be where black holes are. And so I imagine these hypothetical intelligent entities in the future of the universe, probably not us, I don't think we'll last that long, black holes will be where the action is. They'll be all huddled around black holes, and whipping energy out of black holes, harvesting their spin to power their civilizations, and doing weird imaging experiments with the bent space-time around them. And who knows what they'll do? Black holes will be, the center of the universe in a metaphorical sense when it's old.
Do you think by that time the Big Bang Theory will have been replaced?
I mean, there's always a chance that the Big Bang, the whole thing is rotten at the core and will collapse on itself. So, again, if we're putting odds on it, I mean, different people will put different odds. I know very confident people who just think it's essentially not conceivable that it's wrong. I mean, I'd put 5% odds that it's wrong, maybe 10% if I'm feeling nervous. The question is, as a practical matter, as a scientist, you have to know what you're going to replace it with. And as theories mature and get more sophisticated and have more evidence behind them, the evidentiary bar that any succeeding theory has to clear gets higher. And so it's not a question of whether it's wrong or right. I think it looks right at the moment, and we don't have strong evidence that it's wrong. But everyone who comes along, every smart young Turk of theoretical astrophysics who comes up with a new theory, it's got a high bar to clear to explain all of that evidence that sits on the pile of the Big Bang, making everyone feel pretty good that it's the theory of the universe.
Chris, thank you so much for talking to me.
That was fun. Thanks a lot.
For more debates, talks, and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.